Well, thank you, Ray. Yeah, the very fact that I was brought back from last year, I must have done something good last year. So I have a few things that I'm going to talk about. Since some of you heard my story last year, I'm going to talk about energy fundamentals to begin with, because it is a very important topic. We all need to understand the scale of energy, what solutions exist, and how ExxonMobil is looking at energy transition. So that's the first section I will talk about. And then, as Ray mentioned, zoom into some of the technologies, exciting technologies that we are working on in carbon capture storage, biofuels, and one slide on hydrogen, and then close it with some key takeaways. So the chart on the left plots UN Human Health Development Index, and I think Senator Zweigert showed this already in some way, form, or shape, but I think this is a better chart, as we were joking earlier. But the y-axis is showing the Human Development Index, and the x-axis is showing energy use per capita. The circle is for each country, and the size of the circle is proportional to the population of the country. And as you can see clearly on the chart, that as economies develop, as economies prosper, as the standard of living improves, the energy use per capita goes up. So United States is on the right-hand side. The country that I grew up in, India, when I was growing up, electricity was not guaranteed. 25 years after I left the country, things have improved quite a bit. And the chart on the right is the underlying cause for it, is the growth in the middle class. And there are about 3 billion people in the middle class today, expected to grow about 5 billion, so another 2 billion in the next 10 or so years. And that's what is really fueling the energy demand increase, which is driven by standard of living increase. Now let's talk about the scale of energy. So in the world today, about 550 quads of energy used. So this is quadrillion BTUs. 1 BTU is when you burn one matchstick, that's 1 BTU of energy. When you drive 10 miles, it requires about 1,000 BTUs of energy in a car. And this is 10 to the 15, so quadrillion BTUs of energy. The scale of energy is massive. And in the next, from now to 2050, the expectation or estimation is the energy will increase, the demand will increase about 25%. If you look at GDP growth at the same time, it's about 100% increase, so almost double. The reason why energy is not increasing at the same rate is because of energy efficiency. We have been very, very efficient using energy and continue doing on that path. And in fact, if you see the OECD or the developed nations, the energy demand actually is expected to go down, whereas most of the growth in energy is in the developing nations like India and China. The chart on the right is showing the problem of anthropogenic emissions. There are about 35 gigatons of CO2 that are emitted in the world today. Now, it's supposed to peak. If you just take into account what ambitions have been announced, nationally determined contributions, it's supposed to peak somewhere around 2030, 2035 timeframe, and then expected to start going down from there. But if you really believe the net zero ambition by 2050, that has to come down to zero on a net basis by 2050. So it is a massive challenge. And the recently released report by IPCC, if you are on this trajectory, the total temperature increase will be about 3 degrees C versus what we need to really put it down under 2 degrees C or 1.5 degrees C. So this is what we call the dual challenge. Now let's talk about solutions. So this chart shows you all the solutions that are out there. And the first message or comment I will make is all these solutions are important. We need all the solutions. The way we look at it is the x-axis. What can we bring to the table? What capabilities we can bring to the table? So if you start on the right-hand side, we have been in the oil and gas business. So the first line of business for us is reducing the emission in our own operations, and that's what we are focusing on. I'll talk a little bit more about that. Then if you move to the left, there are certain adjacencies where we bring a lot of capabilities, and that's what I'll talk about. So carbon capture and storage is a proven technology. We have been doing that for the last 40, 50 years safely and storing CO2 in the ground. So that's a technology we are focusing on. Hydrogen, as earlier speakers talked about, is an important solution. There are multiple colors of hydrogen. We are focusing on the blue color and some of the variations of the blue color. I'll talk about that. And then biofuels. That is a solution that is needed for heavy-duty transportation. Now, all the other solutions we are not currently focusing on because we don't have any capabilities and we don't necessarily bring to the table, but as I said, they are important as a part of the solution. So this slide shows you our ambition. So we have, as a company, declared a 2050 net zero ambition, say by 2050. Also, 2030, we have certain goals. So in our operations, methane emissions are a key thing that we can go and attack. We have multi-pronged strategy to reduce methane emissions in our upstream operations. So these high bleed valves, equipment that leak methane, we are going after that. So we are going to replace all these valves, 100% of those in the next year or so. The second thing that we are doing is doing the leak tests, fugitive emissions. We really don't know where these emissions are coming from. So we have done millions of leak tests, and we have another three-pronged strategy there. Clearly on the ground, putting in sensors and making sure we understand where those leaks are coming from. In the air, where we have drones and other equipments, really measuring where these emissions are coming from, and in the space. So we are using satellite technology to understand the plumes and detect these emissions. So that's a three-pronged strategy for methane emissions. Similarly, we have an ambition to reduce the flaring to the extent to get to net zero. And as I mentioned on the previous chart, all solutions are important, which is what we are looking at. So we have developed these roadmaps, starting with energy efficiency as the first tranche, then electrification of our equipment as the second tranche, and then these new technologies, emerging technologies like carbon capture, storage, hydrogen, and biofuels. So let's talk about carbon capture and storage. As I mentioned, ExxonMobil has been doing carbon capture and storage for the last 40, 50 years. We are the leaders in this technology. Most of the carbon capture and storage is associated with our oil and gas operations in enhanced oil recovery for high concentration CO2 capture and storing it under the ground. Now, we are number one in the capture, about 9 million tons per annum. We are number two, both in transportation and storage. Now, if you look at the technology pieces of this, the concept that we are going after is really what we call these hub concepts, because it's much more efficient to capture where the emission sources are concentrated. And Houston, as an example, is a great example where many of these emitters, and the chart that the map that is shown there, the circles, the blue circles are the emissions in industrial operations. And it's a hub because a lot of emitters are in the Houston area and the Gulf Coast. The storage space is right there near where the emissions are. So our Houston hub project that we are looking at is actually capturing these emissions and then storing them right there in the Gulf Coast. Yesterday, we made an announcement in the Louisiana region for the first large-scale carbon capture and storage project. It is going to capture emissions from an ammonia producer, CF Industries, to the tune of 2 million metric tons per year, and then store in near where the emissions are in Louisiana itself. Just to give you a quote, the 2 million metric tons is equivalent to removing 700,000 cars, gasoline-fired cars on the street, which is higher than the current sales of electric vehicles in the United States. And that just gives you the scale at which one project can impact of CCS in terms of emission reduction. So let's talk about the technologies. Carbon capture and storage is really a systems approach. What you need on the left-hand side, you can see that emissions are coming from multiple sources. So you have emissions from industrial operations, which range from anywhere from 5% to 15%. The emissions that we have been capturing in our oil and gas are very high concentration for CO2 in the incoming stream, and those are essentially 5% or less high concentration. Most of the emissions are in industrial as well as the power sector. And power sector is even lower concentration of CO2, which is anywhere from 2% to about 6%. And it requires different technologies to capture as the CO2 concentration changes because the costs also change. So there are three elements that are required for the technology. The first is material. You need a selective material, and the material has to be even more selective when the concentration of CO2 in the incoming stream is lower. So direct air capture, which I'll mention in just a minute, requires a very highly CO2 specific selective material to capture the CO2 because the concentration is 400 ppm. Then you need a contactor to efficiently contact the incoming CO2 stream with the material, and that efficiency becomes important. And then you need a process that really integrates all these elements together and integrates the heat in the most efficient fashion. And then you capture the CO2 and then sequester it under the ground, or you can utilize it. There are no examples today of utilization at scale, but that's where emerging technology can really help of how can you utilize the CO2 or just sequester it under the ground. So the three technologies that we are working on with some of the partners that we are really excited about. The first one on the left is shown, as I mentioned, direct air capture. We are working with a company called Global Thermostat on a technology. Again, just to give you some understanding, to capture 1 ton of CO2 from air, you have to process 1,700 tons of air. That's the scale. 1 ton of CO2 capture, you have to process 1,700 tons of air. So you really, really need to be efficient and require less energy to do that because it's a lot of air that you have to process to get. It's like finding a needle in the haystack. But the exciting piece is we have some materials that are a lot more active, and that's what the exciting piece is, and trying to scale that technology at a larger scale. The second technology that we are working on is carbonate fuel cell. And this is interesting because it's a process intensification and higher efficiency version of carbon capture. And while it is capturing carbon, it is also producing power and it is producing hydrogen, which can be used in our operations. And that's what improves its efficiency. So carbonate fuel cell is a technology we have been working on that over 5 years with a company called Fuel Cell Energy. And then we are looking to demonstrate that technology at one of our plants in Rotterdam in the next few years. And the last technology I want to highlight is really focused on materials. It's really in the lab at this point, but metal organic frameworks, we have a collaboration with University of Berkeley. There was a recent paper published in Science, and the material offers a huge opportunity because the material can be tailored, it can be steam generated, and it really offers capacities almost 6 times than what is available today, which will improve the efficiency. Those are some of the 3 projects that I wanted to highlight that we are really excited about in the carbon capture space. Now let's talk about biofuels. The previous speakers talked about hydrogen, battery storage, and other options, but we believe that a liquid fuel is going to be needed for hard to decarbonize sector like aviation fuel because of the energy density. None of these other fuels or energy sources come close to a liquid fuel energy density on a volumetric basis. And that's our hypothesis. So we have a 3-pronged strategy. First generation feedstock, these are canola oil, camelina oil, vegetable oil that are available today, or unused cooking oil, which we can process, either co-process or modify, repurpose our existing assets, the refineries that we have, to make biofuels. And these are low emission fuels that can have lower carbon intensity. So that's the first tranche, is we are looking into reprocessing as well as repurposing our own assets. But the feedstock is limited and it competes with food. So that's where the second generation biofuels come in. These are woody biomass, municipal solid waste. There is a lot more feedstock available in the second generation, but technology has to come along. It's not at scale today. And that's the second piece that we are working, is really working with partners, trying to take this technology that have been demonstrated at a smaller scale and then scale it up, like gasification or pyrolysis, for example. And then the third tranche is third generation fuels, which we have been working over the past 10 years, like algae biofuels fits in that, e-fuels taking CO2. And so we have some technologies in-house and working with partners to work on that. But all this, there's a project that was announced in Strathcona as an example. This is attached to our Strathcona refinery. We are repurposing an existing asset to take canola oil, which is locally sourced, and then use our existing facilities, which have been repurposed, to make biofuels or renewable diesel in this case, which is 100% biofeedstock. And that is a 20 kilo barrels a day project. Our ambition is to go to 40 KBD by 2025 in our circuit, and then to about 200 KBD by 2030. And onto the ramp beyond that. So this is again exciting. Biofuels remains a key focus area for us, similar to carbon capture. The third area I wanted to highlight is hydrogen. And this is a concept similar to the hub concept that I talked about in carbon capture. The left-hand side of the figure is showing you could capture carbon, but in many cases, these industrial operations have distributed carbon streams. So you will have to put a carbon capture kit on all these emission sources in a refinery or a chemical plant or an industrial complex. And it becomes very inefficient to do that at the smaller scale or medium scale. And the efficient way to do it is actually replace or fuel switch with hydrogen instead of burning natural gas. And that's what is shown on the right-hand side, where you produce blue hydrogen at scale from the natural gas, capture the carbon dioxide from the blue hydrogen facility, store it under the ground, and then use blue hydrogen or hydrogen as a source for your operations. And that is a much more efficient way of reducing emissions, because you can capture it easily at a lower cost, as well as use fuel switch to a zero emission fuel like hydrogen. And that's what we are doing a demonstration as well as a project in Houston attached to our Baytown refinery in conjunction with the Houston Hub project that I talked about, which also has the carbon capture. So it is a blue hydrogen and a carbon capture and storage project in the Gulf Coast in the Houston area. So all this we cannot do alone. We are partnering all across the pipeline, from all the way from discovery in the lab with universities. There are a few universities shown there. We collaborate with about 80 universities all across the globe. And we take concepts from the lab and try to scale it up. We are collaborating with startup companies in the middle who have different ideas and different technologies. The two examples that I gave you is direct air capture with global thermostat, and then carbonate fuel cell with fuel cell energy. And then what we do best is do it at scale. I mean, that's what ExxonMobil brings to the table, is take the concepts either from the lab or small companies and do it at scale. So that's what we bring to the table. So partnership and collaboration is key and is going to be very key going forward. So that brings to the closure. So I have three key messages in the key takeaways. First thing is the move to lower carbon solutions is going to require all sorts of solutions. And each party needs to bring their capabilities, their advantages to the table to really be a part of the solution. The second is consistent investment in research and development and technology is going to be key. The point I'll say is, if you read the IEA report, it says that 50% of the technologies that are needed to get to net zero by 2050 are not even demonstrated yet. and 75% are not demonstrated if you look at hard to decarbonize sectors. And that's the challenge. So technology, research and development is really, really important. And the last point is collaboration and partnerships. Nobody can do it alone, and that's where partnerships are important. So I'll stop there. Thank you for listening, and thank you for staying this long on a Friday.
Thank you.